So what we're starting in this chapter are Taylor polynomials. So in real life, a lot of things cannot be integrated or taken the derivative of. So like if we wanted to integrate, I'm trying to find why my pen's not working. E to the x squared dx. This is not integrable. If there was an x out in front, it would be integrable by use substitution. So a lot of things in life are not integrable. So what we want is a way to approximate these functions, because a lot of the times we don't need an exact value. If we're 5 decimal places within accuracy, then that's good enough for most things. So a Taylor polynomial is kind of like an expansion of the tangent line. So the first thing, the tangent line you can do, so if I'm going to find the tangent line of e to the x at x equals 0, so then you find the derivative, you plug it in, and you get the tangent line. So here's a picture of our tangent line, and you can see it's exact at this point because that's where we built our tangent line. If we're asking for an approximation at 2, this is the error. So you can see that's a fairly large error, and as we go further from where we made our Taylor polynomial or our tangent line exact, it would be better. Better when you get close, worse when you get further away. So right here, approximating this at 1, we see, I'm sorry, 1 is there, yeah, which would be right here, I guess. It's halfway in between that one I would looked at 2. This is the error. So the error is less than 1. So that's not bad, but if I go further away, it's going to get worse and worse. So what Taylor did was said, hey, why not do more than just a tangent line? So if I match the tangent line and the second derivative, it would be better. So that's like matching the constant, the first derivative, the second derivative. So we go through and we take 3 derivatives. And again, we're building this all around 0. In the Taylor polynomial, we say that's centered at 0. That's just where it's exact. So I plug in where it's 0. Now this first one's going to be my constant term. The next one's going to be my linear term. And the third one's going to be x squared. So when you go through there, it's derived in another video. I just don't want to do it in this video also. But the Taylor polynomial in general is your function, then the derivative of your function x, plus the derivative of function 0, x squared over 2. Because we want it to match every single way, every single place. So if I take the derivative, I would have f prime of 0 plus f double prime of 0, x squared over 2. And if I'm plugging in 0, I do in fact get just the f prime. Then if I look at the second derivative, what happens is now I have a 2 out in front. So if I didn't divide by 2, then the second derivative wouldn't exactly match the polynomial's second derivative. So each time you're going to have your derivative, your power, and then the factorial on the bottom. So looking at this, you can see that our approximation did get a lot better just with adding the second derivative. So here's our, why is that not erasing? Well, here's our function right here. So looking at that, you see how small the error is. If we're approximating at 1, it's only this tiny little bit right there. So you can see that our error went down to 0.218. So definitely smaller. And that was only matching the second derivative. So we go through and we match the third derivative. And again, we picked e to the x because it's easy. The derivative of e to the x is always e to the x. If we're evaluating it at 1, then all of them, evaluating it at 0, they're all 1. And again, the first one's your constant, then your linear, then your x squared. So there's your Taylor polynomial. And if we look at the error, that's the error in the approximation. So remember, the error in the approximation is going to be the real value minus the approximate value, and the error is always a positive value, so make sure that's an absolute value. So we did get a lot better. It's right here, it was 0.2, and now we're down to 0.05. If we wanted to make this even better, what we could do is now match the fourth derivative, or the fifth derivative. Now, so our Taylor polynomial we just built was the polynomial for e to the x. So think about this. If I was doing some calculation, I would probably only need it to be smaller than this for most cases. So we would just keep this polynomial, and this is one of the ones we're going to memorize. So when I think of e to the x, everybody's positive, and everybody's coming to the party. So you got 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Now this Taylor polynomial is actually called a Maclaurin polynomial just because it's centered at 0. If it's not centered at 0, then we call it a Taylor polynomial. If it is centered at 0, you can either call it a Taylor polynomial or a Maclaurin. So the formula looks really bad. This is the one we just derived with e to the x. So if you look at this each time, you got f0 right here. Oops, not that one. You got f0. And the next one will be f prime of 0x, so the first derivative times x. Then the next one is the second derivative, x squared over 2 factorial. The next one would be x cubed with the third derivative over 3 factorial. So each time when you build a Taylor polynomial by the definition, you're going to have 3 things that you're going to keep track of: the derivative, the power, the factorial. The only difference with it not centered at 0 is that you're going to plug in a for all the derivatives. And now you need x minus a because you're always going to have x minus where it's centered. So in general, this would be the nth derivative at a, x minus c to the n over n factorial. So the next couple problems, we just go ahead and create them. So here we want a Maclaurin polynomial. Remember, Maclaurin means it's centered at 0. And we're going to find the Maclaurin polynomial for sine x. So the first thing we do is go down and take the derivative. So here we have the cosine of x, and then the derivative sine, this one's the sine. So cosine minus sine, it keeps following. We're going to plug in 0. So you can see that a lot of them are zeroing out. And here we have a constant, then that would be your x squared, x cubed, x fourth, x to the fifth. So if we build our Taylor polynomial using the definition right here, f of 0 was 1. F prime of 0 is, f of 0 is gone. That was 0. F prime of 0 is 1. So now you're going to have 1 times x. The second derivative is gone, so we do not have a second derivative over here. The third derivative is -1, so that goes right here. So -1 x cubed over 3 factorial. The fourth derivative is zeroed out. The fifth derivative is 1 over x to the fifth times 5 factorial. And you can easily guess the pattern now. So each time we're going up, we're doing the odds. So the next one's going to be plus x to the 9th over 9 factorial minus x to the 11th over 11 factorial. If you remember from pre-calc, sine was considered an odd function for a couple reasons. We have an odd function means that f of negative x is going to equal to negative f of x. That's true because we have sine of negative x was equal to negative sine of x. The other thing that all odd functions have is origin symmetry. So when I think about origin symmetry, it's kind of a double reflection. So this one right here, I'm just going to keep this piece. If I reflect it around the x-axis, it's over here. But then if I reflect it around the y-axis, it's over here. You see how it has origin symmetry? So when we think of sine x, always think of odds. So the next one we build is cosine. So here we got the cosine x, so we do the same thing. It starts with cosine. So the derivative of that is minus sine, minus cosine, so forth. And again, this was a Maclaurin polynomial. So Maclaurin means that we're centered at 0. So you can see those values coming out. Cosine of 0 is 1, sine of 0 is 0. Keeping track of each of the things, here's your constant, your x squared, x cubed, x to the fourth, x to the fifth. What you notice about cosine is all the odd powers are going to zero out. So this is the polynomial for cosine x. From pre-calc, we knew that cosine was even. So being even means f of negative x is equal to f of x. Think of an even function. Isn't that true? If I plug in negative x, I get f of x. And over in the odd, if I had this problem, if I plugged in negative x, I'm going to get negative f of x. That's also true with cosine. Cosine of negative x is x, cosine of x. And even functions are symmetrical with the y-axis. So you can see right here, cosine is definitely symmetrical with the y-axis. Now notice if you take the derivative of cosine, you're going to get sine back. So here you got minus x plus x cubed over 3 factorial, and so on and so forth. So the derivatives work for the Taylor polynomials also. So now we're just going to build a couple of these. So here we built one for square root of x. We're going to do the third degree Taylor polynomial centered at x equals 4. So since I want the third degree Taylor polynomial, I'm going to take 3 derivatives. So I go over here and I take 3 derivatives. The next thing we do is we evaluate where it's centered. It's centered at 4 this time, so that's what we plug in. So the square root of 4 is 2. And same thing, we get all of these values. And remember, this is your centered, this is your linear. But since this is your constant, so this one's linear. But since it's centered at 4, you need the x minus 4. And the next one would be the x minus 4 squared. So you take the constant, then you take the first derivative, first power. Second derivative, second power, second factorial. Third derivative, third power, third factorial. If you want to think of the function, the Taylor polynomial is totally consistent because I could write right here over 1 factorial, and I can write this over 0 factorial because 0 factorial is defined to be 1. So it's very consistent. You're going to have the function, the power, the factorial, the derivative, the power, the factorial. So we used this above Taylor polynomial to approximate f of 5. So all we're going to do is plug 5 into everywhere there's an x. So we'll have 2 plus 1/4, then you have 5 minus 4, minus 1 over 32. 5 minus 4 squared over 2 factorial. So when we do that, we get this as our approximation. So this is an approximation. So I took this and put this in my calculator, and the calculator is also an approximation. They gave me this. So if I subtract those, the error is less than 0.001. That is less than a 0.1%, or I guess a 0.2% error. That's fairly good for approximating something. We can also do this not just from taking the derivatives, they can give us the values. So here, they gave us a bunch of things to work with. They told us here's the constant value, here's the derivative, here's the second derivative, here's the third derivative. So we can just put those in the Taylor polynomial. Now we know this is centered at 2 because that's where we know the information is coming from. So where you're centered is where you're exact. So we have our constant term. Notice we do not have a linear term. It was 0, so the linear term is missing. -2, -1. So that's the second derivative, the second power, the second factorial. Now remember, I didn't write the second factorial right there because 2 factorial is just 2. And just to remind ourselves, 3 factorial is 3 times 2. You just keep multiplying each integer down to 1. All right, so then here's our third derivative, our third power, our third factorial. So here we use the value to approximate f of 2.1. I just changed it to make it get a little bit closer. It says I go to 2.1, this is our Taylor polynomial. But looking at this, what I want to know, does this function have a max, min, or neither at x equals 2? Now we can only determine that where it's centered, because where it's centered is the only place it's exact. Everything else is an approximation. So think back to Calc 1. How did you know if you had a max or minimum? The first thing you needed to check is if it was a critical point. And it's a critical point if the first derivative is equal to 0. So right here, I know the first derivative is equal to 0 right here. I also know that from the Taylor polynomial because we do not have a linear term. So that's gone. So it is a critical point. I don't know why it's not letting me with this. So it is a critical point. So now we need to check if it is a maximum or minimum. So we can't do a number line on here because, first of all, I don't know the entire polynomial, nor can I plug everything in. So there was something else in calculus we knew if we looked at the second derivative. It tells you about the concavity. So here, we're looking at the second derivative right here. We know the second derivative was -1, which means the second derivative is less than 0, so it's going to be a relative max. And you need to say by the second derivative test. And of course, if the second derivative is greater than 0, then it would be a maximum. And again, just making sure that you understand this, does f have a relative maximum neither at x equals 3? That's not where it's centered. I can only determine if it has a max or min where it's centered. Everything else is an approximation. The polynomial is exact where it's centered. It approximates everywhere else. Here's a table with the ones that we need to memorize right now. So kind of think about it because it's not as bad as you think. E to the x, positive, everybody come to the party. Now think about this. This is x cubed over 3 factorial. The next one would have been x to the 4th over 4 factorial. Then x to the 5th over 5 factorial. So in general, this would be the general term in terms of n. So here, you see that we'd have x to the n over n factorial. And if we plugged in 0, you would have x to the 0 over 0 factorial. Remember, x to the 0 is 1, and 0 factorial is defined to be 1. So we do get this first term. If we let n equal 1, then you're going to get x to the 1 over 1 factorial. And you can see we have that exactly right there. If n is equal to 2, you would have x squared over 2 factorial. And you can see that right there. So memorizing that is going to make things a lot easier later. The next one we have is sine x. And we already talked about sine x was the odds, and it alternates. So you always think odd. Sine x is odd. Now, how would I get an odd power? I can't just do n because that's going to give me odd and even. Well, I know if I do something times 2n, that is always even. So if I want odd, I can do 2n plus 1. Now notice, it alternates, so the next one's going to be negative x to the 7th over 7 factorial. Again, what's ever at top is on the bottom. So I force my power to be even. There's my factorial, and there's my alternating. And again, you can go through and check it. If n is equal to 0, you get negative 1 to the 0, x to the 2, 0 plus 1, all over 2 times 0 plus 1 factorial. That's going to leave you with x over 1 right here. If you plug in 1, you're now going to get x cubed over 3 factorial. You can do the same thing with cosine. It's the evens. So as we go through, you can notice that you're going to only keep the evens, so negative 2 to the n. And the last one is a different kind of build. It's the geometric model. So when you look at this, you're going to think it looks slightly geometric because this is a geometric sum right here. So we know that our first term is going to be 1. Our r is going to be negative x because remember, this is 1 and we need a minus here, so you have to force that to be negative x. Also, remember geometric, you go a, then you multiply by r, then you multiply by r, the common ratio. So if I start with a, which was 1, I multiply by the common ratio, which was negative x. I multiply by the common ratio, which is negative x. And we get this formula. Another way we could have done it is we know the general term for a geometric is a, r to the n. The a is 1. The r was negative x to the n. And I just like to separate it because sometimes we're going to need to see them separated. So this is the same thing as negative 1 to the n, x to the n, because you can distribute that power. Now, I haven't talked about this, but I just wanted to have it all in one place. That is the interval of convergence. So we go through, we practice a couple of these over here. So we found the P5 Taylor polynomial for sine. Remember, what is sine? Sine is the odds. So you start with x minus x cubed over 3 factorial. It says P5, so that means we want the degree to be 5. So plus x to the 5th over 5 factorial. And if I wanted to find out where it was at 1.5, that's what we plug in. We plug in 1.5 for all the x's, and I get this value. So I took the same value and I put it in here to get the exact value. Remember, it's not exact because a calculator is an approximation. But if I look at the difference of those, look at the error. That's pretty remarkable considering we only took 3 terms. Now, I know sine x is not hard to deal with, but there are other functions that are r. So this could be extrapolated to much harder things that we could not have been able to solve. So if I wanted to find the same polynomial, but this time I'm going to do it at 2. So I'm a little far from where we're centered. Remember, we were centered at 0. The first one I approximated was 1.5. The next one we're going to approximate is 2. So again, I'm doing the P5 Taylor polynomial, which would be right here. We're centering at 2. I mean, not centering it, we're evaluating it 2. So this time we're going to have 2 minus 2 cubed over 3 factorial plus 2 to the 5th over 5 factorial. So this is my approximate value. This is my real value. So here's my error. Notice, as we got further from where we were centered, the error got more. So the further you get from where you're centered, the error is going to increase. The more terms you keep, the error will decrease. So it's kind of a balancing act. So the further you are away from the center, the greater the error. And we'll talk about this later. Okay, some of the kind of funky problems. So here it says they gave us a P2 Taylor polynomial. I guess it's Maclaurin because it's centered at 0. Second degree Taylor, centered at 0. We want to know the signs of what A, B, and C are. So let's remember what a Taylor polynomial looks like. It would be f of 0 plus f prime at 0 x plus f double prime at 0 x squared over 2 factorial. So the first thing we're looking at, f of 0 is going to be the constant A. Over here, there's where the constant A is. Oops, sorry, no, 0, sorry, my bad, wrong place. At x equals 0, our function is right here. So then we're going to go through, we know that A is now less than 0. So now we want to talk about the tangent line. So the tangent line would be our first derivative. And when we look at that, we draw a tangent line right here, we see that it is negative. So we know B is negative. C talks about the concavity. You can see it's concave up, so we know C is greater than 0. So sometimes on the AP test, they like to make you match things like that. This time, they gave you a Taylor polynomial, and they want you to go back and find the derivatives. So again, let's remember what it looks like. This would be f of 3 plus f prime at 3, x minus 3, plus f double prime at 3, x minus 3 squared over 3 factorial, 2 factorial, and so on and so forth. All right, so f of 3 is going to be 4. That's the constant. The next one we look at is f prime. So f prime of 3 is going to live right in front of the linear term, but there's no linear term. So we know that f prime of 3 has got to be equal to 0. Then we go to the next one. Now we're going to look at the second derivative. Now right here, what's in front of this is the second derivative divided by 2 factorial. So right here, negative 5 is the second derivative divided by 2 factorial. So if I want to know what the second derivative is, I have to multiply by multiply by 2 and get negative 10. Now, if you went through and took the derivatives, it's going to work out that way. So you could have gone and take the derivatives of this T3 Taylor polynomial. But sometimes they might say, what is the nth derivative? So you have to look at the patterns and understand that the number in front is not just the derivative. The constant in front is the derivative divided by the factorial. So again, looking at the next one, we want to find what f prime of 3 is. So I know f prime of 3 factorial is 6. So then you have to multiply both sides by 3 factorial. So 6 times 3 factorial would be 6 times 3 times 2, or 36. And again, does this have max, min, or neither at x equals 3? Well, we know that x equals 3, the derivative is equal to 0, which means it is a critical point. We know the second derivative is negative, so it is concave down, and it's a relative max. Last, remember, you could only do this where it's centered, where it's exact.